So now we've covered the psychological phenomena we want to understand and the physiology and the anatomy that have to be related to the cognitive phenomena. What I'm now going to do is to get into a rather more theoretical section, and we're going to be going over the constraints which exist on the architectures of complex learning systems. And by complex learning system, I mean a system that has to learn lots and lots of different types of behaviors. When I talk about architecture, I mean the way in which the physical information processing resources of the system are organized in order to perform the functions and features of the system effectively. In other words, the way in which transistors are organized in an electronic system, or neurons in a brain. We're going to touch on systems in which all the features are designed under external intellectual control. In other words, the electronic systems that human beings are constantly using, because there's some lessons from these electronic systems that we can carry across to systems like brains, which have to learn most of their behaviors. But most of our time will be spent on complex learning systems like the human brain. And this discussion is pivotal to the course, because it's these constraints, enforced on the brain by natural selection, that make it possible to understand how all the brain anatomy we've just gone through results in the cognitive phenomena we described at the beginning of the course. And I'll be reminding you of some very basic first principles of computer system design, because we need to examine how these basic principles apply in modified form to the brain. As we discussed in the first lecture, the physical resources of an electronic system are arranged in a hierarchy of modules. The modules at different levels are printed circuit assemblies, integrated circuits, standard cells, transistors, and sometimes we even have to be able to understand transistors in terms of the behavior of electrons in a regular array of silicon atoms with occasional impurity atoms. The reason we can achieve system understanding is that we can view what the most detailed modules are doing as the performance of instructions and the manipulations of data. And we can view what higher level modules and even the system as a whole are doing also as the performance of instructions and manipulations of data, where the instructions performed at high level are combinations and sequences of more detailed instructions and so forth. The key point being that we're using common information processing paradigms at all levels. To understand how system features work, we have to be able to describe large chunks of system behavior with a small enough amount of information that a human can hold all the information in mind at the same time, so understand the behavior. But because of the limited amount of information, the descriptions approximate to some degree. At a more detailed level, we can describe behavior more precisely, but because of the much larger amount of information needed, we can only think about small parts of the system behavior at one time. At high level, you might want to describe how to play a video game. At a more detailed level, you might want to describe how to update the display fast enough to keep pace with the changing game images. And at a very detailed level, you might want to describe how the processor instructions determine which pixels need to be changed next. So we have to be able to map between these levels. The common information models make it possible to do this mapping, so we can establish an intellectually satisfying understanding of the system, which allows us to do things like repairing a system or making modifications to its design. So the critical question is whether such a hierarchy of description exists for the brain. In other words, can we relate higher cognitive phenomena, like creating a painting, to activity in different anatomical structures, then to neuron activity, and ultimately to neurochemistry? For this to be possible, there must be some hierarchy of descriptions that will allow us to understand on a high level, approximately, but map that understanding in stages down to much more precise, detailed descriptions. So the key question is, does a hierarchy like this exist for the brain, or can it be created? To approach that question, let's think about why we need to understand electronic systems, or how do we use such understanding? Because, if you like, the need to design the system, modify it, and so on, these are important reasons why we have to understand it. And there's another important consideration. All this has to be done without requiring excessive amounts of information processing resources. I'm bringing this up because, as we'll see shortly, there are all sorts of conflicts between these different considerations, and it's the conflicts that strongly shape the resource architecture. Let me put this a little bit differently. There are some practical needs that must be met for an electronic system, and unless the system architecture is organized in certain ways, we won't be able to meet those needs. And the interesting thing is that requiring the system to be organized to meet these needs is pretty much equivalent to requiring an organization that makes understanding possible. Most of these needs are fairly straightforward. When we modify a system, we define the feature change we want at high level, but the implementation of that change has to be at a much more detailed level. We may have to change detailed components like transistors or integrated circuits or specific lines of software code. And furthermore, those changes, those detailed changes, mustn't affect any of the features we don't want to change. So to do all that, we have to be able to map from a high-level description of the desired change to a detailed description in terms of electronic components. Repairability is really almost the same as modifiability. If the system fails, there are high-level symptoms. Some features don't work properly. But to repair the system, we have to be able to map from those high-level symptoms down to more detailed level where we can make the necessary component corrections. Then, to be practical, a system can't need huge amounts of resources, or it'll be too expensive. And a critical point here is that there's some conflicts between, for example, modifiability and resources. If every feature used completely separate resources, then we could modify one feature by changing its resources in the appropriate manner without worrying about the effects on other features. But if features share some resources, you have to worry about side effects. But limiting resources means that some resources will have to be shared between different features. All the features may have to use the same processor, for example. One commonplace example is the code bloat that sometimes occurs in large software systems. If intellectual control over a system has been lost and feature changes are still needed, it's very hard to determine what software code changes will implement a new feature without generating lots of bugs in other features. So the solution is to make a copy of the software code, keep one copy unchanged, and modify the other copy to support the new feature, and only call on the modified copy if the new feature is needed. But of course, that can lead to exponential growth in lines of code. I'm actually old enough to remember when 50K of RAM was regarded as a bit excessive for a personal computer operating system. I'm sure there's a lot more features in today's operating systems, but are there really enough features to justify 100,000 times as much RAM? I tend to believe that that kind of growth means the designers have lost intellectual control over their system to some degree. There's large parts of the system that nobody understands anymore. Now, synchronicity is a bit more complex, but it's really an aspect of resource conservation. I'm discussing it separately because it turns out to have a very strong impact on architecture. So what do I mean by synchronicity? Well, any system is going to get a constant stream of input states over time, one after another. And it's going to need to process the information in each state. But Because processing takes a certain amount of time, there will generally be information derived from states at a number of different times being processed by the system all at the same time. Information from different states mustn't be confused. Now, you could avoid confusion by processing every input state using different resources, but that's going to need too much resource, even if you only have to handle sequences of 3 or 4 input states. So you have to find a way to avoid confusion, even though simultaneous processing of information from input states at different points in time may be taking place in the same resources. The final need is a bit different. You have to be able to build lots of copies of the system from some kind of design specification. If the construction process is very complex, building a system will be very expensive and may result in lots of errors. So you need to keep the construction process as simple as possible. So these are the practical needs that you can also view as reasons we have to make electronic system architectures understandable. But it turns out that natural selection imposes some very similar needs on brains. A species with a brain that can learn new behaviors without damaging its ability to perform behaviors that it learned earlier will have a considerable natural selection advantage over a species in which previous learning is lost when it learns something new. A species with a brain that can recover to some degree from damage, like a stroke for example, that species will have a natural selection advantage over a species in which any damage is irreversible. If some species has a brain that can learn a given set of behaviors with fewer resources, like neurons, than the brain of another species, the species needing fewer resources will again have a considerable natural selection advantage. It won't have to find as much food to feed its brain, even though its brain performs just as well. At any point in time, there may be several objects in the sensory environment of a brain. A species with a brain that can process information derived from multiple objects using the same neurons but not confusing the objects will have a natural selection advantage over a brain that gets them confused or needs more neurons to avoid confusion. Brains have a construction process. They need to develop from DNA blueprints. A species with a brain requiring a complex and error-prone construction process will be at a disadvantage. And there's a requirement for brains that isn't really relevant for electronic systems. Evolution to improve the ability to respond to the environment is based on random mutations. Some mutations are beneficial and are therefore favored by the selection process. But a mutation may also degrade something. A brain with an architecture in which almost any mutation has catastrophic side effects will not be able to evolve. So a brain architecture in which not all mutations result in serious deterioration in some function will again have a natural selection advantage. So, analogous with electronic systems, brains have a number of constraints on their architectures imposed by a number of practical considerations.